Hello, and welcome to Exponential Functions. My name's Tuesday Johnson. Here's an introduction to a concept. Let's look at the laws of exponents. If b and c are positive, and x and y are any real numbers, then we have the product rule that says b to the x multiplied by b to the y is equal to b to the x plus y. We have the quotient rule that says b to the x divided by b to the y is b to the x minus y. We have the reciprocal rule that says 1 over b to the x is equal to b to the negative x. And I'm just going to add one here. If we have 1, where did I go? That's not where I meant to be. If I have 1 over b to the negative x, that's the same as b to the positive x. So anytime you cross the fraction bar, you are going to be changing the sign of the variable, right? The exponent, not the variable, the exponent. Power of 0, b, as long as b is not 0, b to the 0 is 1. If I have a power raised to a power, that I multiply. If I have the power of a product, so if I'm multiplying two things and I raise it to a power, that's the power on each factor. And the same thing with the quotient. Now, something to keep in mind here. Let's go for a pen and let's make this. Let's see if purple works for us. I like to think of this using the order of operations. Property number 1 says that if you're multiplying two things, you'll add the exponents, right? Quotient rule says if we're dividing two things with the same base, always with the same base, we'll subtract the exponents. Here in number 5, it says if we have an exponent raised to an exponent, we'll multiply. So if you think of the order of operations in kind of this tier-like level, you can see that exponents step down one step on everything we have here. But when we get down here to the power of a product and power of a quotient, notice there's nothing below this. So if I have b to the x plus b to the y, that's it. We cannot simplify. If I have b plus c to the x, there's nothing I can do. I can't simplify. There's nothing below add and subtract on the order of operations, so we're not able to simplify those in the exponents. All right, so order of operations is kind of your structure here to keep these laws straight. So let's look at some exponential functions and their graphs. An exponential function is a function in which the variable occurs as the exponent. For example, f of x equals a times b to the x, with a and b real numbers, a not equal to 0, b positive, right? Can't be 0, can't be negative, but not equal to 1. And really, if b is equal to 1, 1 to any power is just 1, so it's kind of boring. It's a constant function. Now, there are 4 basic graphs depending on the sign of a and the value of b. Keep in mind, b has to be positive. So in our first example, if a is positive and b is larger than 1, we'll have a graph that increases rapidly. Some might say exponentially. Right, and it'll be all positive, non-negative. Down here we have an asymptote, meaning the graph doesn't actually touch the x-axis, but it gets super close along the way. If a is positive, our graph will still be above the x-axis, but now if b is a proper fraction, a fraction between 0 and 1, my graph will be decreasing. If my leading coefficient is negative, all of my answers will be negative answers, and if b is greater than 1, it'll look exactly like our red graph, only flipped over the x-axis. There's something there. There's a reason for it. And if a is less than 0, we'll have negative results, and a fractional value brings our graph closer to x equals 0 the further out that we go. Okay, it's all about a fractional value, a proper fraction. We get close to 0 the bigger the x is. If b is bigger than 1, we get further away from 0. Further away from 0. There we go. So let's look at the roles of a and b. For the exponential function given by f of x equals a times b to the x, when x is equal to 0, we'll have f of 0, which equals a times b to the 0. Well, b to the 0 we saw in our rules is just going to be 1 because b can't be 0. So any non-zero value to the 0 power is 1. 1 times a is a. So right here at the the y-intercept will be the value of a. This is our y-intercept. All right, so a has a role. The base b has a full name of base multiplier. I like referring to it as a base multiplier in class too because it tells us exactly what it does. For each single unit increase in x, the y value will be multiplied by the value of b. All right, so in linear functions, we added or subtracted. Here in exponential functions, as we increase x by 1, we're going to multiply the y values. Let's look at some examples. We want to determine if the table describes an exponential function, and if so, we're going to sketch the graph. So here we have our x values, -1, 0, 1, 2, 3. We call this numerical, right? It's in a table. My y values are 2, 6, 18, 54, and 162. The first thing I look at is my x values are going up by a consistent amount each time. Awesome. X values going up consistently. Remember, exponential functions multiply by a certain amount each time. So what do I multiply 2 by to get 6? Well, that seems like a 3. And what's 6 times 3? Oh, that's 18. So it looks as though when x increases by 1, my y value is multiplied by 3. And you can check it. Pretty sure that the base is 3. We know that the y-intercept is always when the x value is 0. So at the point 0, 6, a value is 6, b value is 3. I could write my equation and graph it. Desmos, for the graphing, makes a very nice output. Let's do another example. Here we see that our x values are increasing by 1 each time, but it looks like the b value is getting smaller. So I'm dividing by 3 each time, right? 27 divided by 3 is 9. 9 divided by 3 is 3. 3 divided by 3 is 1, and so on. But remember, we want a base multiplier. So instead of dividing by 3, we say that we multiply by 1/3. All right, the y-intercept right here is when x is 0, y value is 9. Tells me my a value is 9. And we'll have our equation. Y equals 9 to the 1/3 x. Here we see our y-intercept of 9. The graph is decreasing because the base is a proper fraction. You might also see this, right? The reciprocal, if I want to switch the order of my fraction, all I have to do is offset it by a negative in the exponent. So there are several different ways that you could write these exponents depending on what it is that you're trying to show. Let's look at number 3. Again, x is increasing by 1 each time. But the y value, 7 times 2 is 14. But 14 times 2 is not 25. 25 times 2 is not 52. And 52 times 2 is not 100. It's not consistent. It's close to 2 each time, but it's not 2. So if it's not consistent, we can't just assume it's close enough to 2. Right? We have a y-intercept. It seems like we could find our a value. But the reason no exponential function is described is because there's no consistent pattern of multiplication in the y values. This is not an exponential function, and so there's nothing to graph. All right, thanks for watching. Don't forget to subscribe. I'm just kidding. Don't forget to subscribe, though, if you want to, because everybody needs some more math videos in their life. And you never know what I'm going to say.